Next operation that we will learn on sets is intersection. Now, what do you mean by intersection? What does this word stands for? The symbol for intersection looks like this, like an inverted U, the opposite of union, inverted U here. And to understand what exactly intersection means, I'm going to take you back to my very first example. So suppose, A is a set of students in your science section who are opting for mathematics, and B is the set of students who are opting for biology. Now, this time, suppose your school is offering that students can opt for both the subjects as well. And suppose there are 10 such students who are opting for both mathematics as well as biology. So out of the 30 students who are opting for mathematics, 10 students are such who are actually opting for biology also. Out of the 50 students who are opting for biology, 10 students are such who are opting for mathematics as well. So now if we draw a diagram to portray this, earlier our diagram was two circles, separate circles, because they had nothing in common. But this time we are saying that mathematics and biology together is possible. So suppose this is the set denoting students who are opting for mathematics, and this is the set denoting students who are opting for biology. Now what are we saying? There are around 10 students who are opting for both the subjects. That means they will be in this common part which is basically a part of M also and a part of B as well. So 10 students are here. If 10 students are here, then to complete this circle of mathematics, the complete circle of mathematics should be 30. So that means here, where I have only mathematics, will be 20, because 20 plus 10 will give me 30. Similarly, there are total 50 biology students, but 10 are opting for maths as well. So they are a part of this intersection, this common area. So 40 are here. 10 plus 40 will give me 50. So that's the notion of intersection, common part. So what is intersection basically telling you? It is the set of all the values from the universal set such that those values are in A and they are a part of B as well. These values are in A and in B. So logically, intersection stands for and. So here I will put my emphasis. Union stands for or, intersection stands for and. So in a diagram, the common part is basically intersection. Now, if you take the example of natural numbers, remember I had taken a set of even natural numbers and I had taken O as the set of odd natural numbers. So 2n minus 1, where n is a natural number. If I may now look at the intersection of these two, odd and even natural number, do you think you have anything in common? Absolutely not. There's nothing in common. Hence, I will get the set of no entries, that is the null set. So intersection of even odd is here, it is 5, which means this will be the situation where the two sets are like this and you do not have any common part between the two. Okay. Now there are certain laws and properties, as we visited in case of union, as we saw certain laws, there are certain laws which are referred to intersection as well. So number one, just like the union, intersection is also commutative. What it essentially means is that if I'm taking the intersection A intersection B and B intersection A, it's going to be the same thing. Why? It will be the same thing because I am talking about the common entries, right? So whether I see A and B or B and A, it's going to be the same thing. Number two, the intersection of a set with itself. Of course, it has to be the set itself. For a simple reason, you are talking about entries which are in A and entries which are in A. That will give you entries which are in A, right? Number three, associativity. Yes, if I change the parenthesis, if I take A intersection with B intersection C, or I take the intersection of A and B first and then take the intersection with C. It's going to be the same thing. Let's see how and why. So I'm going to create a diagram. A's intersection with B intersection C. Now B intersection C is this part. B intersection C is this part. Now you want A's intersection with this portion. If you will say see A's intersection with this portion, you will get this part, which is the intersection of all the three actually. Now let's create the right hand side. So if I first take A intersection B, this is your A intersection B. Now if you take the intersection of A intersection B with the C, the intersection of this portion, the yellow portion with C is this blue portion now, which again means we are talking about the intersection of the three. So this means these two sides will always be equal. The left hand side is equal to the right hand side. That means you can change the ordering of taking intersection. Number 4, if you take the intersection of a set with the universal set, so this is a universal set, and you are taking the intersection of a set A with the universal set. So you will be talking about all the elements that are in A and are in the universal set as well. What will you get? Of course, you will get A itself. So the intersection of A and the universal set is A itself. And if you try to take the intersection of the null set with any set A, so this will have all the elements that are in A and also in phi. There's nothing in phi. So what will you get as this intersection? The common part between phi and A is nothing. So you will fetch phi itself. Now, property or law number 6. If B is contained in A, then A intersection B will be equal to what? This will always happen just the way we saw in case of union. This will also always happen. So we are talking about a situation where you are two boxes. This is box A and box B contains some elements which are in A also and they're in B also. So this is box B. It's totally inside A. So whatever elements you have in B, they are a part of A also. That's what this symbol containment means. B is contained in A. Okay. Now, you are talking about the intersection. Intersection means common part. The common part, that is all the elements which are in A as well as in B, are the elements which are in B. So that means this will be equal to B. In terms of a Venn diagram, it will be this is A and this is B, and B is entirely contained in A. So what is the common part? The common part is B. So hence this will always happen. It's a law when it comes to the operator intersection. Okay. The next very important operation on sets is the difference. So difference is another very important operator. Suppose we have a set A, which is the set of all numbers from 10 to 20. 10 to 20. And B is a set of numbers which is from 5 to 15. B is the number which is from 5 to 15. Now, if I want to take the difference between A and B, so it's like A minus B. When you subtract something, so it is almost like you're taking those things out. So this will be like you are taking B out of A. It's like you are taking B out of A, which means that you will be talking about, you are take all. So A minus B means you take all the elements of A that are, you take out all the elements. So A minus B means you take out all the elements of A that are in B as well. You don't want B to be there in A minus B. You want to take out all the elements that are in A and that are in B as well. So in other words, we are saying that A minus B contains elements of A and only A. Those elements which are only per se in A, they should not be in B. They should not be in B. So suppose we define A minus B in this example. So that means these are the numbers that I have in A and these are the numbers that I have in B. I want to take all the B out of A. So anything that is there in B and it's in A also, I'm going to take that out. So A consists of 10 to 20 and B consists of 5 to 15. Now that means 10 to 15. These are numbers which are there in A also and B also. I don't want these numbers. I want numbers which are exclusively just in A. So these numbers will be 16, 17, 18, 19, 20. Because these are the numbers which belong to A, but they're not in B. So in other words, more formally, if we define A minus B, it is the set of all elements, from the universal set such that X belongs to A and simultaneously it must not belong to B. So which means it belongs to A and only A. Now, if you want to see it using a Venn diagram, that what exactly it would picture as. So you can think this is A and this is B. Everything that is in A, but it's not in B. So which means if you take out the intersection, of A and B, that will give you only A. So A minus B is actually only A. Only A. Similarly, now think about it. Is B minus A same as A minus B? Absolutely not. By the definition itself, if I may just give you this diagram for B minus A. Let's use the same logic for B minus A. Now this is A, this is B. And this time, I just want B, only B, exclusively B, which means all the elements that are in B, but they're not in A. So that means I'm going to take out this intersection. This intersection should be out. So only B area is this, only B. And that's what is B minus A. Clearly, A minus B is absolutely not equal to B minus A. These are conceptually two different things. In first, A minus B, you're taking out B from A. In the second, you're taking out A from B. So it is conceptually two different things. Now, you have certain properties and laws associated to difference as well. And that's what we will talk about here. So number one, if you take the difference of A from itself, that means you are taking entire A out of A. What will you be left with? You will be left with no entries, no element. You will be left with phi. Number two, if you take out phi from A, that means what are you doing? You have a set of elements A and you take out nothing out of it because phi consists of no entries. You take out no entry out of it. That means you will be left with the entire set A. And number three, if you take out the universal set from A, if you take out the universal set from A is a set which is a part of universal set. A is a set, this is the universal set, say. A is a set which is a part of universal set itself. If you take out the entire universal set from it, that would mean that you are taking out all the entries that are in A as well. So if you are taking out universal set out of A, that means nothing will be left. Nothing will be left. No entry would be left. So A minus the universal set will give you phi. With difference, I'm going to introduce you to another concept in set theory, which is complement. Complement of a set. So complement of A written as A, and it's like a superscript here, C. So complement of A. Complement of A essentially means that everything that is in A is not a part of the complement. Or in other words, complement consists of everything which is not in A. So suppose this is your universal set. Suppose this is your universal set and this is A. And this is A. So A complement means everything which is not in A. Everything which is not in A. Or in other words, you take out A. Just take this out. So A complement is everything which is not in A. In the universal set, everything which is not in A. So A complement is this area in the universal set. Now, why I'm talking about complement here is because if you may notice, A minus B, let's represent it again. Let us represent A minus B again. So if this is A and this circle is B, if this is A and this circle is B, we just understood that A minus B is only A portion out of it, right? Only A. If you may notice what is happening here, you can also say that A, only A or A minus B is essentially the intersection of A with B complement. Because whatever here you have in B, if you exclude that, that gives you B complement. If you exclude that, that gives you B complement. What I'm trying to say here is that if you exclude this B circle of B, if you exclude that, all this gray part is B complement. And if you take the intersection of A with this gray part, this is the portion you will get, and this portion is nothing but A minus B. So A intersection B complement is this portion. Okay, a fun fact here. Now, we have seen and we have realized by the definition of difference is not commutative, right? What you can talk about in terms of distributive property. But what is something that we must realize here is that set difference is right distributive over union. So what do I mean by this? Let A, B, C be any three sets. A union B minus C is equal to A minus C union B minus C. So what have we just done here? We have subtracted on the right? So, and we are able to distribute this union operation here. So which basically means that it's right distributive over union. Let's now look at it via a Venn diagram to understand it thoroughly. So suppose this is A, this is B, and say this is C. You have C out here. You have A, B, and C here. Let's try to check what do we have for right hand side and left hand side. So let's check the left hand side first. Let's take A union B. So A union B will be everything that is in A, either in A or in B. Everything that is either in A or in B collectively gives you the union. Okay, so this is union. Now I have to subtract C out of it. If I subtract C out of it, that means I will be taking out this part. I will be taking out this part. This was the C part, right? So which means I'll be left with this portion, only A portion, this intersection, and the only B portion. So everything which is a little yellow-green now, more yellow. So this is your left-hand side. So what you've done is you've subtracted C. So you have cut that C portion. C. Now let's observe the right-hand side. Are we going to get the same thing? And are exactly what we had for the left-hand side, exactly the same scenario. Now we have to see what is the area defined by A minus C union B minus C. So we will have to locate what is A minus C. So you got to take out everything that is in A, which is also in C. So everything that's in A is this. And I have left the portion which is in C as well. So this has been taken out from A. That's A minus C. Similarly, B minus C would be everything in B, which is also in C. So you just take that out. You just take out what is in C. So what you will take out of B? Everything that is in C has been taken out. So what are we left with? We are left with this area. Is this area any different from the left-hand side? Well, clearly what I see here, it's not the case. It is exactly the same. The right-hand side is also exactly the same area as you can see in the two diagrams. Well, so which means what we said is true. The set difference is right distributed over union. It is right distributive over union means A union B minus C is same as saying A minus C union B minus C. This is the only distributive law which will be valid here. And I can make use of something else here which we have learned. So quickly let's work set theoretically. We've seen through Venn diagram that this is happening. Let's work set theoretically. So we have A union B minus C. Now, do you remember I just told you that A minus B, for any two sets A minus B, is equal to the intersection of A with B complement. So that means for any set A union B minus C, it is basically A union B is a set and you have minus C. That means we are looking at the intersection with C complement. We're looking at the intersection with C complement. Now, what do I know about union and intersection? They follow the distributive law. So what I can say that this must be equal to A intersection C complement union B intersection C complement using the distributive law of intersection and union. So this means that what do we have here? A intersection C complement means A minus C. Again, using the same definition. Union B intersection C complement means B minus C. So what do we have here? A minus C union B minus C. And that's what we quoted as our law. So right distributive over union.